Hopefully my screen is visible and we have no echo, I suppose. Is it fine? Okay, just let me continue with this. So tries are order trees. They are trees actually with the following properties. And the property is that the root is not labeled. There is no label for root. No alphabet assigned for the root. And each node has got a label from the character set or from the alphabets. Then the ordering, as I told you, the ordering of the children of all the nodes is in canonical form. Obviously, except the leaf nodes. So all the internet nodes have ordering, which is in canonical form. Now, and now when we are, as I told you, the tries are used for storing strings. For searching, retrieving textual information, or for pattern matching. So how do we find a pattern or how do we match the string is we traverse from or we start from the root node and goes all the way following the path till the leaf node or the external node, and that will give us the string. That is, each node will have the label, and that label, if we concatenate it, we will have a string. Now let us take an example. Suppose this is the set. We have strings. This is the set, and this set has got 8 strings, I suppose. Now these 8 strings has to be now these 8 strings we have to store them in a tree that is known as a trie. So this is our alphabet set or set of characters is nothing but English letters, and we will start first by storing the first string, that is bear. Now root node will not have any label, remember that. Then each character B, we will have a node for B. E, now E will be created as a left child of B. A will be its left child, and R is the last character, so that's the leaf node. So now if we traverse from the root with this path and at the leaf node, follow the path till the leaf node, we will get the string as BEAR. The same way the next string we have is bell. Now here B already we have in the tree, so E is already also there. What we need is LL. Now this LL is not there in the tree. So we will create a node for L. So it will be BEL and then L followed by L. So if we traverse this path BELL, we get the second string. The same way for the third string, B is there. Then we have E as the child, but we need ID. So I will be created as a node, and then D will be created as a node. So if we traverse this path, we will get the string as bit. The same way BULL bull, we have B, so U will be a node, and L and L will be its child and child. Same way by BU we have it. Y will be created as a leaf node or external node. And the next string is cell. Now S is not there. Starting from it's the tree start. This part of the subtree trie is starting from B. So we have S. We create a new node as S from the root, and then we'll have E, L, and L. Now don't worry about this L node L and L getting repeated, because we have to follow the path to get a string. We have to follow the path from the root till the leaf node. So anyway, we will have nodes which may be having the same label. So that is not a problem. Then stock. S is there. We have T, we have O, and then C and K. for stop. K will be the leaf node. That's the third, the last uh, string is stop. We have STO already. So we follow STO and P will be the leaf node for this. So when we take the from the root node, when we traverse each till the leaf node, we get all the strings. So this is known as a trie. Now remember, it's not a binary tree. There may be more than one children. It's not that exactly two children has to be there or less than two, at most two children. It's not a binary tree. It can, a node can have any number of children. Now, as I told you, there are certain things we need to observe here. That is, for S strings in a set, that means there are 8 strings in the set. So S is 8 over here. So for S strings in a set, there will be S leaf nodes. Why? Because from root till the path, if you follow till the external node, we get the string. So if you see, all the rectangle nodes are external nodes, and there will be 8 external nodes because we have 8 strings. We have R, L, D, those are the external nodes, 3, 4, 5, 6, 7, and 8 external nodes. Then the height of the tree will be equal to the length of the longest string. So if you can see here, if you see, this is a 4 letter, 3, 4, 3, 4, and this is the longest string which has 5 letters. So you can find that the height of the tree will be equal to the longest string, the length of the longest string. So this is some of the things we can observe from tries. The other thing is the total length of all strings, that is beer is 4, bell is 4, so it's 8, bid is 3, 9, 10, 11, and so if you sum up all this, actually this statement is little vague here. So I'm just not going to take up this part. Let us delete this part. So anyway, there are 2 things we can observe here for tries. Actually, what the statement was that the total number of will have for the number of nodes, what we are going to have will be equal to the total number of this the length of the string. But that's actually statement was wrong, because we have this tree grows large, and the height of the tree also increases. So anyway, that is solved in the next problem. That is why I had the statement. Now, so if you observe here, the height of the tree will be equal to the length of the longest string. Now the problem using this is these tries are known as standard tries. Now the problem over here is that these standard tries will grow, and there will be some children with only one, there will be some nodes with only one child, and there will be a lot of memory space wastage, because a node with only one child can be clubbed together to save the amount of memory, because trees take a large amount of memory. So these tries are known as standard tries. So what we have is the next thing known as compressed tries. Now compressed tries will try to club the 2 labels or 2 alphabets into a single node, so that the amount of nodes gets created will be much lesser. So compressed tries they are similar to standard tries, but each internal node had at least, that's the constraint here for a compressed tries, that each internal node, remember it's not the leaf node will not have any children. So each internal node has at least 2 children. So what the condition over here is, what we are, the compressed tries does is, if there is one child for a node, that is compressed into a node. so that we save amount of the number of nodes that gets created. So here in this case, what we have is, if you look at this part at the leftmost, we have BEAR. Now, B doesn't matter, it has more than more than one child. E also has more than one child, but A has got only, A is an internal node, has got only one child. So we can compress these two, A and R. So we can compress A and R into a single node. So here in this case, here compressed tries, all nodes will not have only a single character. That's not the constraint here. Constraint is that each node should have at least two children. And this AR becomes the leaf node. Then even LL can be compressed. So it becomes, instead of two nodes, we can compress it to one node. In this case, node I has D as the only child, so it can be compressed. And we can have BID or BEAR. That is how it is. The rest of the things for following the root, following the path from root till the leaf node remains the same. Then here U has two children, so but L has only one child, so this can be compressed and we have L. Then over here we have L. There is only one child for L, so we can compress this into node LL. Once we compress this, we have E, node E. Node E also has only one child with LL. So we can again compress that to make this node as ELL. So there's two times we have compressed it here in this what you call path. And then we have STOCK. The C has got only one child, so we can club it, compress it into CK. Then this part, OT, is also one child. So there are two children for O, but for T there's only one child, so we can compress it into OT, and then these two will become its children. So the difference between the standard tries and compressed tries is that it is compressed tries that each internal node will have at least two children. So from the standard tries, what we can do is whoever has one child, we can club it, or we can compress it into a node, and then it becomes a compressed try. So this will, if you observe from the previous standard try, this structure has got less number of nodes. So obviously it's going to save more amount of space. It's much efficient than standard try. Now the things are same. That is, the observation is same. If there are S number of strings, then there will be S number of leaf nodes. You can check it here. We have 8 strings. The number of leaf nodes will be 8 itself. And obviously that is the condition. Each internal node has at least 2 children. Now, let us move further with the tries. We still have time, no problem. Move further with the tries. Now this compressed tries, you can observe that they are, the nodes storing multiple alphabets or letters. Now this can further be, we can make efficient use of the numbers here or indices here, so that the instead of labeling the nodes, the letters or sequence of letters, we can label them with integers or indices. Now here, if you look at this table, what we have is each string, we are calling that as S, and we are assuming that they are stored in an array. So here in this case, array is starting from 0. So S0 is the first string, which is BEAR. Second is S1, which is BELL, bell. Third is bit, and so and so. And each string itself is an array. So, and which is in this case starting from 0. So we We have labeled this 4 because the largest string what we have is of 5 letters or 5 alphabets. So what we are saying here is from 0 to 4 we have the length of the string, and strings are themselves stored in an array. Now what we can do is we can represent this, the compressed trie, using integers or indices. Now what we will do is, in case of D, we will replace with indices. The first index represents the index of the string from where that letter was derived, or from where that letter has come out. Now first index is 0. Why? Because we have the first B. This B was created for the first string with index 0. So first index what we have is 0. Then the second and the third part, tuple, is nothing but from where that string starts and ends. B is starting from 0, ending at 0 itself. So we have 0, 0, 0. So remember, first is the index of the string, and next two integers or numbers are the indices from where the letter starts, where the substring starts, and where it ends. So B starts from 0, ends at 0 itself. Now, so this is actually represented in terms of k, I, j, where k is the index of the string, and I, j is the index of the alphabets in the string or letters in the string. Now what about E? This E again starts from 0. Why? Because this E is for the first part, has come from the first part. Now E may be there in other places also. We are not bothered. We are just bothered about from where it is coming, how that E was created. So it was from the first string, so 0, and E is from first index and ends at first index itself. So this is 0, 1, 1. This is the index used. Now what about AR? Now AR is from the first string itself. So we have 0, first integer, and then A is starting from 2, and R ending, that substring, is ending at 3. So we have 2, 3, start index and end index of the string. So it is 0, 2, 3. In the same way, LL. Now this LL has come from where? Come from the second string, that is with index 1, and L starts from 2, ends at 3. So what we have is 1, 2, 3. ID, bid, it is from bid. So I is for the string with index 2, so 2, 1, 2. So we will have ID as 2, 1, 2. The same way this same way U, we have U, which is coming from here. It will be 3, 1, 1. Then we have this same way, we can label all the nodes with the indices. So this is how we can use another compact representation, what we call, by using indices instead of strings. Because why we are calling this compact? Because here we have A and R. So we started from 0, 2 to 3. So 2 is start with A and 3 is for R. Now suppose if we have a longer substring, then instead of utilizing the memory here, we can only store that string over here, and then we can just use the start and end index to represent. So all the nodes can be represented as a tuple k, I, j. Whatever the length of that node might be, can be stored in terms of k, I, j. So this saves even more memory space. So that is the reason we are representing the nodes in compact way. Now the next thing we have to see is something known as suffix tries. Now here you can understand suffix. Why we have compact way of storing suffix tries. Now this suffix tries is also a trie. It's not a compressed trie. It's a trie where strings is a collection of all suffixes. Remember that it's collection of all suffixes. Now let us consider the string minimize. Suffix means what? Suffix means something which is added at the end. Prefix is added at the front. Suffix is at the end. So let us try to create suffixes for this minimize. How many suffixes can be there? Starting from E, we can have E. The next suffix can be ZE, then IZE, then MIZE, then IMIZE, then NMIZE, NIMIZE, and finally we can have the whole string that is minimize. This is minimize itself will be a suffix because it's not added to anything, but it's considered suffix because we are learning tries because we want to index the textual information in terms of a tree representation. So anyway, suffix tries are tries where the strings are collection of all suffixes. So here we have a string as minimize and we have created all the suffixes. We have these are all the suffixes. And the set of strings is nothing but all these letters. Oh, sorry, all these suffixes. So we have one E, Z, E, I, Z as a set. Now let us try to create a try. So we start with a root which does not have any label. Then for E, it will be a root node. No, sorry, from root node we create a label as E, node as E. Then for ZE, we will have Z and then E because Z is not there still. So we create a new node. For IZE, I is not there. So we create a node I, then Z, then E. Then we have MIZE. So M we don't have it here. So we start by creating a node M, I, Z, and then E. Then we have IMIZE. We already have I. So the tree continues from here. So we will have I, M, I, Z, and E. Then we have N, M, I, Z, E. We don't have N from the root, so we create a new node or child with N, and then continue with this. The N, M, I, Z, E. And then I, N, M, I, Z, E. So we already have I. So we will start from here itself, continue creation of the whole path till the leaf node. Then we have M, I, N, I, M, I, Z, E, minimize. So M is already there, I is already there. We will start from N, I, M, I, Z. N, I, M, I, Z is already here, but we have to follow the path from the root till the leaf node. So here we have I from MI, NI, MI, and then finally we have Z and E. Z and E. So this is how a try is created for suffixes. For a word or for a string, we create suffixes and then we create a try. Now this try is known as suffix tries, and this suffix try is trying to take, again, takes a lot of space. So we can compress this. Now how do we compress this? This whole thing having only one child, it can be compressed. Obviously, the compressed tries, and I think what tries where each internal node has at least 2 children. So this whole thing can be compressed into one. Then this whole thing also can be compressed into one. And that ZE also can be compressed into one node. The same way NI, MI, ZE can be compressed into one. Then this ZE also can be compressed into one. Then this one, NMI, MI can be compressed into one. This ZE also can be compressed into one node. Then what we have is, still we have to compress this. Why? Because M node, all the nodes have more than more than one child. Hello? Except now node M has only one. So we can compress this also. We can make MI as MI itself, and then the rest of the 2 things will be its children. So this is how we compress them. We compress the entire. You can see that the whole tree has become very, in a representative compressed form, and is known as a suffix tree. Now this also can be in a compact form, because here MIZE, here we have NIMIZE, and then we have NIMIZE. So we need a lot of space to store. We will not be knowing how much space each node will take to store the whole sequence of letters and characters. So here also we can compact it, and let us look at here. But here we will not use k comma I comma j as a tuple. Why? Because it's only one string, and that string suffixes we have created. So here from root node we have E. Where is E? E is starting from Z. So we don't have index for the string. We have index for each character, from where that character starts, where they end. So instead of k comma I comma j, we only have I comma j. So here in this case, what we have is E is at 7th index. So 7 comma 7. Start and end is the same. I is there. I is at first index. So there is at third index and sixth also, but it was for the first index. So MIZE, where is it? M is starting from here, I, but this is not Z, this is N. So MIZE is starting from 4 till 7. So it's not from 0 to 3, it's from 4 till 7. Then we have NIMIZE, so it starts from 2 till 7. So this way, all the nodes can be represented in a compact form, and each node will only contain 2 indices. That is start of the index for the start of the character and end of the character. So these were all about suffix tries, or actually tries, which I used in information retrieval. Now, why have we seen tries? We have seen tries because of their uses in information retrieval, and information retrieval has become a very it has become a concept for World Wide Web, where we have huge collection of textual documents, and the information or the data is gathered from web pages through web crawlers. These web crawlers are used by search engines to retrieve relevant information and store that information. The information, whatever is stored by the search engine, is in a dictionary form. And those are called as inverted files or inverted index files. And each word in the dictionary is nothing but it's called as an index term. And based on those index terms, we have based on the occurrence, we have the ranking, which is stored in an array. So the number of occurrence there will be an array which stores a list of the terms and their occurrences. So what we have seen, the strings which we have created, and tries what we have created, it's nothing but for information retrieval. The terms which are there for web crawlers, the search engine stores from the web crawler, the keywords which are taken from the web pages used by through web crawlers, those terms are stored. Array stores the occurrences of them, but terms actually are stored in compressed tries so that it can be easily written. So this is the reason actually the application of tries is nothing but nowadays as the search engines which tries to use them. So this is what we have. Actually, I thought of completing the AB trees as well as B trees, but the lab was open a little late. So that is the reason we could not do it. Anyway, it doesn't matter. In the next class, we'll try to complete that. Now, if you have any questions, you can ask me, or we can